Hello, my name's Thanom and I'm from UNSW. Today I'm going to work through some of the MATH1011 calculus questions from this section on the applications of integration to mechanics. So question 1 here is giving us the velocity of a particle which is moving in a straight line. So it's given us velocity in terms of time here. We're told that the particle was at the origin at time t equals 0. So that means x equals 0, its displacement was 0 initially. And it's asking for us to find the distance of the particle from the origin. Well, the distance of the particle from the origin is simply the displacement. And we want that at time t equals 2 here. So the idea is that we're given velocity and we wish to find displacement. Now we know displacement differentiates to velocity, so that means if we have the velocity in terms of time, that will integrate to give displacement. So let's do that. We've got our velocity, or dx dt, is given by the equation 2 plus 2t minus 3t squared. So if we just wish to find an equation for displacement, that's just going to be an antiderivative here, or we can write that as an indefinite integral here. So displacement differentiates to velocity, velocity will integrate to give displacement. So here that's 2 integrates to 2t, 2t integrates to t squared, minus 3t squared integrates to minus t cubed there. And we have to plus a constant here because we're not quite sure if there's an extra constant. We have to use the information they gave us, and that was that the particle was initially at the origin, to calculate what this constant is. Now it turns out that at t equals 0, it was at the origin, so x equals 0, and if we substitute those in, we'll get that 0 is 0 plus 0 plus 0 plus a c, so that actually tells us that that constant is 0. So in fact, our equation for displacement in terms of time is 2t plus t squared minus t cubed, and there is no constant there. Now, to answer the question, we wish to find the distance of the particle from the origin, or the displacement, when t equals 2. So we want to substitute t equals 2 in here. So finding x of 2, that's 2 lots of 2, plus 2 squared minus 2 cubed. Well, that's 4 plus 4 minus 8. That's 0. So it's actually 0 meters from the origin after 2 seconds. So let's just conclude there. So therefore, the particle is 0 meters from the origin. That is back at the origin. After 2 seconds. Okay, so actually it started at the origin, and after 2 seconds it's back at the origin. So that's the end of that question, but I just want to draw your attention to the difference between a question asking where the distance of a particle from the origin, that is its displacement, and a question that asks the distance that the particle travelled for those 2 seconds, right? Because it actually started at the origin and it's back at the origin. It may have travelled somewhere in between, and if we want to calculate that distance, we have to do a little bit more work. So let's continue and calculate the distance that the particle travelled in those 2 seconds. So first of all, note calculating the distance travelled requires more work. In particular, it requires us knowing whether the particle is moving to the right or moving to the left, that is, whether the velocity is positive or negative. If we draw a graph of the velocity function, we'll be able to see when it's positive or negative and decide how to calculate this distance here. So the graph of that parabola for velocity against time looks like this. 2 seconds, it's got a negative velocity here. At 0 seconds, it's got a velocity of 2. Turns out that this intercept here is 1 plus root 7 all divided by 3. So you can draw the graph of this concave down parabola here. We can see that the velocity is positive from 0 to 1 plus root 7 on 3 seconds, and we can see that it's negative here. So it starts off moving to the right. At 1 plus root 7 on 3, it stops and turns around, and then it moves to the left from that point onwards. Seeing just on a one-dimensional picture what's happening to its displacement. It's starting at the origin at t equals 0 seconds here. It's moving to the right until 1 plus root 7 on 3 seconds, and that's when it stops and turns around. I might even draw it like this. It stops and turns around, and we know that it's back at the origin at 2 seconds just from this calculation that we did over on this side. So this makes sense. It's moving to the right, stops and turns around, moves to the left, and that's why it can be back at the origin. Its displacement can be 0 after 2 seconds. If we want to calculate the distance travelled, we need to know its displacement here. We need to know where it is at 1 plus root 7 on 3 seconds. We can calculate that because we have an equation for displacement. The equation for displacement is 2t plus t squared minus t cubed. So if we calculate 2t plus t squared minus t cubed, then we will calculate its position, its displacement there. Now that's approximately 2.1 or 2.1 meters, let's say. So this is 2.1 here. It starts at the origin, which is 0, which means the distance it travelled was just 2.1 minus 0. So that's 2.1 here. Given it was back at the origin, it travelled 2.1 back as well. So in this case, therefore the total distance travelled from t equals 0 to t equals 2 is double that 2.1, or 4.2, let's say, meters. So it's approximately 4.2 meters that it travelled. So that was a nice calculation just because it started at the origin and ended up at the origin there as well. So calculating distance requires us knowing the direction the particle's travelling in. Calculating the displacement, or the distance from the origin, we simply need to know the equation for the displacement, and we can substitute in the time that we need to calculate that displacement for.